Just a few more seconds. Okay, we are now live on YouTube and we are video recorded. So please, Ezra, you can take over.
Thank you, Tom. Welcome back, everyone. And we continue in the OpenGeoHub Summer School. And now it's my pleasure to introduce Sandra Di Iaco. Sandra Di Iaco is full professor in statistics at the University of Salento in Italy. Her research interests include spacetime covariance modeling and multivariate geostatistics for environmental data. And the topic she will talk about today is modeling spatiotemporal dependence. Sandra, the floor is yours. I think you can share your screen.
Okay, thank you. Okay.
Yeah, we can see it. Maybe you can full screen it.
Okay. It is already full screen, maybe. Ok, non posso farlo, no. Okay.
Yeah, looks good.
Oh, that's fine. So thank you, Ed, and welcome everybody. It's a pleasure for me to take this seminar, and I will hope that it will be of interest. In this presentation, I will touch different aspects, starting from a brief introduction on stationarity, covariance properties, and an overview of some classes of space-time covariance variogram models. Then I will focus on the main problems of modeling choices, and I will provide some hints useful for the model selection, which regard behavior near the origin, asymptotic behavior of the covariance, full symmetry and separability, type of non-separability in case the covariance function is non-separable, and some application on studying or computing the type of non-separability. Then I will go into details of the testing procedure, together with the statistical tests, which can support the selection of the appropriate covariance model. At the end of a case study where the testing procedure has been applied, and moreover, for further details, I have provided a list of references that the participant can use. Regarding the summer school challenge hackathon, the task I've posted in my channel is referred to the construction of an interactive location map, from which the spatial couples to be used, for example, for analyzing full symmetry, separability, and so on, can be easily selected. The winner will be announced at the end of this day or at most tomorrow morning. Thus, please upload your solutions on my channel. So let's start briefly. Introducing the space-time random function that is denoted with Z of ST, where S belongs to a spatial domain, capital D, and T belongs to the temporal domain, capital T. In geostatistics, the observations of a phenomenon that develop simultaneously in space and time are interpreted as a finite realization of Z. This theoretical characterization can occur in nearly all areas of applied environmental natural sciences, such as hydrology, climatology, meteorology, earth sciences. And in many situations, the spatio-temporal pattern of the environmental, the natural processes involved presents on one end a systematic structure at the large scale, often described by deterministic model denoted with M, and on the other end, a stochastic behavior at the macroscopic level, described by a random field denoted with Y. where the expected value is supposed to be equal to 0. For this aim, the space-time random field Z is decomposed, is usually decomposed in the sum of the two components, the M component and the Y component, the deterministic and the stochastic component. Here are just a slide regarding the definition of stationarity. Very briefly, if second order, if a space-time random field Z is second order stationary, it means that we suppose that expected value is constant and the covariance depends only on the spatial temporal legs HS and HT. Okay, and in case of second order stationarity, also the variogram depends on the spatial temporal legs, HS and HT, and you can see the definition of the variogram. And then under the second order stationarity, there is a relationship between the covariance and the variogram as given in 6. In addition, after introducing the spatial temporal covariogram and variogram, it is important to define also the marginal. The marginals denoted with the C of HS0 and C of 0 HT, which are respectively the spatial covariance, marginal covariance, the temporal marginal covariance, and analogously the spatial marginal variogram gamma HS0 and the temporal marginal variogram gamma 0 HT. We will see that marginals will be very useful in the estimation stage. As known, it is often convenient to assume also the intrinsic hypothesis instead of second order stationarity hypothesis, since these hypotheses, the second order stationarity hypothesis, do not require that variance, the variance and the covariogram exist and are finite. So the intrinsic hypotheses are weaker hypotheses with respect to the second order stationarity hypothesis. Under the intrinsic hypothesis, the expected value of the difference of the two random variables separated by the spatial temporal legs HS and HT is equal to 0, and we suppose that the variogram depends on the spatial temporal legs HS and HT. We already know that the spatial temporal dependence, the spatial temporal dependence is the main focus of this presentation. The spatial temporal dependence is studied through the covariance function or the variogram function of a process of a random field Z, supposed to be second order stationary. The covariance is a similarity measure between the two variables, Z of S T and Z of S plus H S T plus HT. And the variogram, on the other hand, the variogram is a dissimilarity measure, which means that it increases as the distance increases. It is known also that the covariance model has to be positive definite, which means that it has to satisfy the condition in 9. Note also that if the quadratic form in 9 is strictly positive for any choice of the points and for the coefficient lambda not all 0, C is said strictly positive definite. Strict positive definiteness is preferable for spatial temporal prediction, since it in some sense ensures the existence of a unique solution for the Kriging system. Similarly to the covariance function, even the variogram has to satisfy a similar condition given in 10. Regarding the main properties of a covariance function, we can say that the covariance is not negative, in the origin. It is symmetric and is bounded, which means that its graph is in between minus C of 0 and C of 0. From the convexity property, if C sub 1 and C sub 2 are space-time covariances, then both their sum and the product with the positive constant are covariances in the same domain, in the space-time domain. This is also true for the variogram, which means that the sum of the variogram is again a variogram. If we make the product with the positive constant, we get again a variogram. From the first stability property, if C sub 1 and C sub 2 are space-time covariances, their product is still a covariance in the same space, in space-time. And then from the second stability property, the integral of a spatio-temporal covariance function with respect to a positive measure is again a covariance function on space-time. Okay. Let's go through these specific other properties. If a space-time random field Z is assumed to be, in some sense, a function of independent components defined on separate domains, the analyst can use one of the following separable models, as in 11 and 13. The factorized separable covariance obtained through the product of the covariance functions defined on the separate domains, or the nested structure covariogram obtained through the sum of the same elements. Okay. So differently from the properties that we have seen before, in this case, we are making the product of covariances defined on separate domains. So it's not the product of space-time covariances, but the product of covariances defined on different domains. Most space-time covariance or variogram models have been in the literature derived starting from the factorized covariance or the nested covariogram. For example, the product model or the linear model, or also called the nested model, belongs to this category. As will be specified hereafter, the nested model, however, will be not strictly positive definite, but only positive definite. But we will underline this after. Here, a list of some classes. Of course, is not an exhaustive list of covariance model, but just few models that are available in the literature. Among them, the metric, the separable, and we will see them into details in a moment. So let's start from the metric model, which requires the use of a metric in space-time. And the coefficient A sub 1 and A sub 2, in some sense, allow to work with spatial temporal coordinates with different physical units. Otherwise, space and time cannot be compared because they are expressed in different units. One of the drawbacks of this model is that the same type of model is assumed for the spatial and temporal covariances, the spatial profile and the temporal profile of the spatio-temporal surface, covariant surface. Only possible changes in the range are admissible. The linear model, one of the old model presented in the literature, built as the sum of the spatial, the only spatial, and the only temporal covariance functions. As I said before, this model is for certain configuration of points is just positive definite. It is not strictly positive definite. And then we have another separable model, which is the product model, obtained just multiplying the only temporal and the only spatial covariance functions. In this case, if C sub S and C sub T, the two marginals, are strictly positive definite, then the whole model, the space-time model, is strictly positive definite. However, this class is severely limited since for any pair of spatial legs or temporal legs, the space-time covariance has the same shape. So it's in some sense proportional. And this is the product model in terms of variogram. This is interesting. This form is interesting because in the variogram version of the product model, we can see the sum of the two marginals, but also the product of the two marginals. We have the sum minus the product of the two marginals. So it's weird that we, from the separable covariance, we get this form in terms of variogram. However, this form is very, very interesting, very, very useful in the application, in the estimation stage. Okay, and here the product sum, which is obtained by combining the linear model and the product model by using the coefficient k sub 1, k sub 2, and k sub 3, for which k sub 2 and k sub 3 are non-negative, and k sub 1 is strictly positive, which represent a sufficient condition for positive definiteness of the model. Even for this model, if the two marginals C sub S and C sub T are strictly positive definite, the whole model is strictly positive definite. And here the version of the product sum model in terms of variogram. And it's nice to see that after modeling the marginals, the spatial marginal, the spatial variogram, marginal variogram, and the temporal marginal variogram, the user, the analyst, has to just estimate one parameter, which is k, and which depends only on the spatial seal, the temporal seal, and the global seal. So it's very easy to be fitted to the empirical surface. And here, just an example, just to show that there is some relationship between this class of models. So the metric model, the product, for example, if we consider, for example, the metric model, and we assume that C is correspond to the exponential model, then the metric model is equal to the product model. And if we use an alternative metric, the metric model is the product of the two exponential model. And if we consider this relationship between the metric model and the product model, then the product sum can be considered as a generalization also of the metric model. And the sum metric, which is applied, is commonly applied in the literature. It is obtained by combining the linear model and the metric model, as we'll see even this in this formulation. We have the parameter alpha that, in some sense, allow the comparison between space and time. Okay. And here the integrated product or product sum model that are obtained by using the second stability properties. And here, the covariance in the integral can be the product or the product sum. For example, in 28, we will see the expression where the expression 27, where we have substituted to the covariance C sub ST, the product sum model. And here the integrated product or product sum in terms of variogram. So we can get models, spatiotemporal variogram also by integration, by integrating spatiotemporal variograms. And it is interesting to underline that although the product model is separable and integrable, the integrated version of the product model can be non-separable and non-integrable. And this is a characteristics of this model. And from this point of view, we can distinguish the integrated, for example, product model from the Crécy model that we will see now, the Crécy-Wang model, which is supposed to be integrable. So a difference between the integrated product model and the Crécy product model is the integrability of the two models. Then here we have the class of model proposed by Ma, where we have a mixture, a positive power mixture of spatial and temporal correlation functions, as in 30 and 31. In some sense, this can be considered as a special case of the integrated product model. And here the Crécy-Wang obtained by recalling the Bochner theorem. However, it depends on the closed form Fourier inversion. So it's very limited from the practical point of view. However, if the autocorrelation rho it depends only on HT, this model can be reconducted, is equal to the product model. And here the knitting model based on the use of completely monotone functions, C and phi. Although this model, the knitting model, are in general non-separable, it is possible to associate the spatial and temporal structures to the function psi and phi, as we can done in the product model on the product sum model. Even in the knitting model, there is in some sense an association between the phi and the psi function with the spatial and the temporal structure. The knitting model do not recall the Bochner theorem, so as Crécy models do. So it does not depend on the closed form Fourier inversion. So it's easier to obtain from a practical point of view a wide range of classes of spatiotemporal models. At the end, the Stein model, based on an extensive class of spectral densities, even in this case, in few cases, we can have a closed form of this class or explicit expressions for the class of these models. So let's start talking about problems and hints in modeling choices. When a sample covariance function or a sample variogram have to be modeled, we have to face, first of all, the problem of the admissibility of the model. For this problem, it is enough for the user to select a valid model from the ones that we already know to be positive definite. So it's not necessary for the user to check the admissibility of the model. Just pick the model from the list of the valid models. And the other problem that we have to solve is the problem of the model selection, which is related to the identification of the appropriate covariance or variogram model type for our data. The selection of an appropriate class of models might be based on its geometric characteristics and theoretical properties, compared with the empirical features presented by the sample covariance function. So the idea is to know the features of the theoretical model and analyze the features of the empirical surface and compare these features. For this aim, it is useful to look at the behavior near the origin, the behavior at infinity of the covariance, to check full symmetry and separability, and the type of non-separability, and all these aspects can be useful to decide the appropriate model for our data. And the use of the marginals, variogram, and the use of the statistical test can support the user in the choice. Okay. Regarding the behavior at the origin, we can say that regarding this behavior, a model could be convex in both space and time, convex only in space and concave in time, or vice versa, or concave in both space and time, as illustrated in the three figures. In most of the cases, looking at the marginals along the space and the time, the spatial and temporal axis, help is of some help in order to decide the type of behavior near the origin, if it is convex or concave. And this is the same graph in terms of variogram. Here we have some examples. In example one, the covariance model is obtained from the knitting construction by assuming that phi is exponential and C is the Cauchy model. And the parameter A and B are just non-negative scaling parameter, something related to the ranges in space and time. And the parameter alpha and gamma determine the smoothness of the covariance function. From alpha, and depending on alpha and gamma, the behavior near the origin could be linear or parabolic. For example, if alpha is equal to alpha and gamma is equal to 1, this means that behavior near the origin is parabolic, convex. If alpha and gamma are equal to 0.5, the behavior near the origin is linear, which means concave with respect to space and time. In example 2, the product sum integrated class is obtained by assuming that C sub t and C sub s to be integrated are the stable models, powered exponential, also called the powered exponential, and we get the product integrated class in 36. In example 3, we have two classes obtained from the Crécy-1 construction. Even in this case, we can recall the parameter. We can see the parameter A and B, which are non-negative scaling parameters, and also with respect to the behavior near the origin, we can see that the covariance function 38 is linear along the spatial axis and parabolic along the temporal axis. You see in 38 that HT is squared and HS is just linear. Okay. Regarding the continuity at the origin, we can say that by construction, the metric model, Crécy-1 and knitting are continuous at the origin, unless a nugget effect is added to the model. Otherwise, the linear model, the product sum model, the product sum, the integrated version of this model are continuous if the marginal structure which generate the model are continuous at the origin. So if the marginal continuous, the spatiotemporal models is also continuous. Similarly, the symmetric model for which the spatial or the temporal nugget effect or a joint nugget effect can be included in the model. With respect to the behavior at infinity, what can we say with respect to the behavior at infinity? Spatiotemporal variables may or may not present the same variability along space-time. What does it mean? This aspect influences, in some sense, the asymptotic behavior of the associated space-time covariance functions. For example, the linear model, the product sum model, or the integrated version of the product sum, also the symmetric model, are suitable to model variables characterized by different variability along space and time. This means that the marginal might not decay at infinity. Otherwise, the other model, metric and product knitting, for example, are often used for describing, for modeling variable characterized by the same variability along space and time. However, they can cover if we choose suitably the marginals. Even from the product model or the integrated product model, we can obtain model that can describe variables characterized by different variability along space and time. We can obtain different alternatives for all this class of models. And here some other example. For example, for the knitting class, just to show you that if we use, for example, the knitting class, according to the choice of the psi function, we can get a model that decay at infinity or not. For example, in theorem 1, we have the knitting model for which the function psi goes to infinity, phi goes to infinity, and the knitting model decay at infinity. Look here, if we compute the limit of phi and it goes to infinity, the limit is equal to infinity, then the covariance decay, the spatiotemporal covariance decay. On the other hand, if we consider the stable model, if we consider the case where the limit of psi is equal to a constant k, not infinity, but the limit is equal to k, then we can see that the covariance does not decay. Decay when we consider just the limit over hs, but not the limit over ht. Maybe it is easier if we consider an example here. Here an example where the knitting model is characterized by the same variability along space-time, which means that the surface, the covariant surface, and the marginals decay. Both decay. So this model is able to describe variables characterized by the same variability along space and time. While in this other example, we obtained again with the knitting model, we can have that the marginal in time does not decay, but it gets stable around the constant, while the marginal in space decays. Okay. But we have started, in both cases, we have started from the knitting class. In one case, the marginals and the surface decay, and on the other case, one of the marginals does not decay. And here, even the integrated product model can be used to describe variables characterized by the same variability in space-time, or even by different asymptotic behavior along space or along the space and time axis. And this depends on the covariance function C sub S and C sub T that are integrated, as can see in corollary 3. In some cases, the marginal, the spatial profile, the temporal profile decay. In some other case, gets stable around constant. This is an example of integrated product. As you can see, the marginal decay and even the surface. And in this other case, look at the limit here. Does not decay. Even in the spatial and the temporal do not decay. Okay, and this is another example. And this is a graphical representation of the product sum model, where you can see that this class reflects the presence of different variability along space-time. The marginal gets stable around constant. Even the marginal in space and the marginal in time. This is a specific characteristics of the product sum. Even the sum metric. The marginal gets stable around constant, to not decay. And so let's go a little bit on the features of the property of the covariance. Regarding the full symmetry and separability, we can provide the definition. A stationary space-time covariance function, C, is separable if it is equal to the product of the two marginals over the variance. Or equivalently, a spatiotemporal covariance function rho is separable if it is equal to the product of the two marginal covariance correlation functions. A stationary, on the other hand, a stationary space-time covariance function is fully symmetric if it is invariant with respect to the sign of one of the legs, which implies also the last chain of equality. So symmetric if C of HU is equal to C of H minus U. And many statistical tests can be used to support the choice of the appropriate model. Many statistical tests can be used for checking symmetry, separability, or the type of separability. In particular, the test based on the asymptotic normality of the covariance estimators can be applied by using the CovaTest package. And I've also posted a vignette for this package, if you like to use it, if you like to use this package. Okay, if the covariance function, if our covariance model is not separable, it is interesting to evaluate the type of non-separability by computing, first of all, by computing the non-separability index, and then by testing the type of non-separability with appropriate statistical test. That's the definition. About the definition, we can define the index of non-separability as the ratio between the correlation function rho and over the product of the two marginals, the spatial and the temporal marginals. Consider that this ratio depends on the lag, the spatiotemporal lags, and on the vectors of parameter theta. And the spatiotemporal covariance is uniformly positive, non-separable, if this index is greater than 1, or uniformly negative is if less than 1 for any spatiotemporal lag H and U, and any value of the parameters theta, or just pointwise positive or pointwise negative if the ratio is greater than 1 or less than 1. And if this happens just for some spatiotemporal lags or some values of the parameters specified in theta.
Sandra, can I briefly interrupt you?
Yes.
So we are 5 minutes before the end of your presentation. I hope that your slide counter at 51 of 90 doesn't mean that you. I
will go very, very fast in the last part.
No. We're not going very fast in the last part. We have 5 minutes and we have a few questions that we want to discuss. So I'm sorry about that.
Is it just one correction? It's not a 5 minute. It's a 20 more minutes.
Yes.
Oh, hang on. Oh,
yes, because
I'm sorry. I'm so sorry. Yeah. It's.
Oh no. Sorry about that. Sorry about
Sandra, please continue.
A quarter after past 4, right?
Yeah. You have quite a past.
Just
4.
continue.
Sorry about that.
Yes.
Sorry. Yeah.
Yes. Okay. Anyway, I will be fast and in the last part.
No.
Okay. Uniformly, I'd like to underline that uniformly positive non-separability implies the pointwise positive or negative non-separability, but the converse, of course, is not true. And of course, taking into account the type of non-separability, the class of covariance models can be classified with respect to the type of non-separability. For example, we have seen that in different papers, we have seen that the knitting class is uniform positive, the Cressy-Wang and the integrated product can be positive or negative depending on the parameters of the models. The product sum model is uniform negative, non-separable, and the product sum integrated model cover different options. So it's very flexible from this point of view. From a practical point of view, as I said to you before, we have just to take in mind that on one end we have the characteristics of the model, on the other end we have the characteristics of the empirical surface. So we know the characteristics of the model. What about how to study the non-separability on our sample covariant surface? From a practical point of view, we can compute the sample non-separability ratios given in 46, which is obtained just as the ratio of the sample spatiotemporal correlation function and the product of the two sample correlation marginals. And if the sample ratios are overall greater than 1 or less than 1, uniformly positive non-separable or uniformly negative non-separable are preferable, class are preferable. So we look at the sample ratios. If it is greater than 1 for all legs, we can choose a class of model which is uniform positive or uniform negative. On the other hand, if we have a sample ratio which is greater for some legs, greater than 1 for some legs, and less than 1 for other legs, it means that space-time covariance classes which are non-uniformly separable should be selected. It means that it's better to select a model, a class of model which are non-uniformly non-separable, like, for example, the product sum integrated model. even from a practical point of view, a diagnostic tool like the box plot of the sample non-separability ratio classified for spatial and temporal X might be useful for the analyst, for the user, in order to detect the type of non-separability of our covariance, of our sample covariance, as we can see in some examples here. And here we have, for example, a case study that regards PM10 daily data from the dataset Airbase. Thus, the above mentioned aspects, like the behavior of the spacetime sample covariance function, are analyzed. The figure here shows the sample spacetime covariance surface and the two marginals. It is clear from the graph that the linear behavior near the origin. It is also clear that we have different variability along space and time. Look at the spatial, for example, spatial marginal covariogram, that it gets stable around 60, and while the temporal marginal gets stable around 20, more or less. So different variability along space and time. Then we have computed the index of non-separability, and we have built the box plot of the ratios classified for spatial legs and temporal legs. It is clear from the graph that the index of non-separability is overall less than 1. Which means that, for example, the product sum model is appropriate for this case, because the product sum model, we already know that is uniform, negative, non-separable. Okay, so the empirical check is strictly related to the choice of the model that we are going to select. And here we have another case study regarding hourly average of NO2. We have the spatial profile, the temporal profile, and here we have the box plot classified for spatial with respect to spatial and temporal legs. In this case, the index of non-separability is not overall greater than 1 or less than 1. So this means that for this case study, for this data, it might be useful to use a non-uniform, non-separable model, like, for example, the integrated product sum or the integrated sum metric, for example. And what about the testing procedure, the statistical test? We have already seen what can we do just looking at the empirical results. But we can just use the statistic. We also use the statistical test to test full symmetry, separability, type of inseparability, and also the appropriateness of some classes of spatiotemporal models. Here you have this is to show you the sequence of the steps aimed at selecting a suitable class of covariance models for the data, symmetry, separability, and then type of non-separability. And then if a non-separable model is convenient, then the type of non-separability should be analyzed. And then, as you can see here from this flowchart, this is the procedure that starts from the computation of the non-separability index. Then it follows with the statistical test on the non-separability. And here I have also some theoretical slides on the test, but we can discuss on for example, the theoretical aspect regarding the test during the discussion, if you like. So I can, if you like, I can stop here before the theoretical aspects on the test that you can see, for example, from the Libo test, the Libo paper of 2007, or my paper in 2011 or 13. And then I will open the discussion on this presentation.
Good. So there are a few questions that we can now then discuss. There are two in the Zoom chat. One of them is that the comment, more of a comment, that this is the paper, the presentation seems somewhat abstract. Well, you know, in any case, compared to the previous two presentations. And could you share some references later that it is for us easier to understand it further? Do you have like the reference, like for instance the one here, or the reference to your own paper? Are they in your slides, and are your slides also on the Mattermost? Are they also available to participants?
Yes, I can post it, of course.
Okay.
Yes.
Okay, that would be great.
Yes.
Then the second question that was asked on the chat, are all these 12 models suited only for Euclidean space, or how to handle more than 2 dimensions?
So is this on the Zoom, on the Mattermost?
Sorry, this is a question that came from the Zoom chat.
Can read it from the chat.
Yes, I was now reading that one.
So are you reading the last one?
Yes.
So the one related to the Euclidean space?
Yes. Are all these 12 models suited only for Euclidean space, and how to handle more than two dimensions?
Yes. You know that we can compute you can compute the distance even for more than 2 dimensions if we are data in a spatial domain, which is in a 3-dimensional domain, for example, plus the time, which is a 4-dimensional domain. We can compute the same model. We don't have limit on hyper-dimensional space.
Mm-hmm. No, the question would be, is it still practical and useful, maybe? The second question is, are these models mostly efficient for strong stationarity, or well extensible to weak stationarity or non-stationarity random fields?
The basic assumption is second-order stationarity. So I assume that the model, the random field, let's say the random field Z is second-order stationarity. So what I say regarding the behavior near the origin, or the asymptotic behavior, and the type of non-separability regards a second-order stationary random field. If we use the statistical test based on the asymptotically normality of the covariance estimators, we have to consider the hypothesis of the Libot theorem, which is based on strictly stationarity, which implies that the probability distribution is invariant with respect to translation, but the distribution function, not the moment, the second order moment. So if we use the test, we have to use strictly stationarity.
The third question on the chat was here: what are your thoughts on Markovian geostatistics, the transiogram concept, and temporal variogram? Are you familiar with that? Do you have opinions on that?
No. Is it on Mattermost?
This is the last question on the chat also.
On the chat. I don't see it.
It's the last part. It follows after this. The last question.
Are this model mostly efficient? You mean this one? Are the mostly efficient for strong stationarity?
Yes, and then follows 3.
And then the point 3.
Yeah.
No, maybe this can be studied. Maybe we can look at it. No, I've never thought about this aspect.
Okay, good. Now I see that other people can't see the chat. Yeah, so the chat is very inconvenient for questions. So let's move to the Mattermost and see if there are other questions, because you were already there. There are not too many questions. I'm going from the last one. I'm going up because otherwise we end up with doing all my questions. So PM Natural asks, based on the presentations, we would need to select one of these models to describe the time spatial structure before deciding how to interpolate using kriging or any other similar methods.
Yes,
no?
Yes, of course. Yes, we can decide the right model before.
Right. Yeah.
Before using kriging for interpolation or prediction. So you have to be sure that you start from the right covariance model or the variogram model, and then use it for prediction purposes, for example, or simulation purposes.
And so I had a follow-up question, or sort of a question that generalized this a little bit more. Now, my experience and sort of we also did some work with fitting these models, and it turns out to be complicated, cumbersome, and very often not very successful. Yes, there's a lot of data set where it is absolutely sort of a terrible job to try to fit one of these models, and you will not end up with really satisfactory results. So could you say something about when this is really needed, or when, under which conditions is it okay to, is it sometimes okay to do purely spatial interpolation of time slices, or to do a purely temporal interpolation of your time series? Could you say something about that? So when is it needed?
Yes, I think that this is the question is if you need a separable model or a non-separable model, which means that it depends on the interaction in space-time. How strong is the interaction in space-time? So how high is the difference between the covariance, the space-time covariance, and the product of the marginals? If the two elements, if the two terms are very far away, this means that there is a strong interaction in space-time. So you need to use a non-separable model, and then you have to decide which kind of non-separable model you have to use, positive or negative non-separable. It depends on the type of the interaction of in space and time. In some cases, the interaction is strong, and then you need to use a non-separable model.
So are you saying that if your covariances are separable, that the interpolation is also separable, that you could do with just temporal interpolation or spatial interpolation?
Yes. I was saying that if your random field is just the product of a random field in space and a random field in time, you could just make your own interpolation in space and time separately, because there is no interaction in space-time. When there is interaction, then you have to think to interpolate in space-time using a non-separable model.
Mm-hmm. Right. I had another question. Yeah, you mentioned sort of the degree to which there are interactions, right?
Yes.
And these, I think, for many people, including me, it is difficult to to get some kind of intuitive feeling what such an interaction, what it means. So could you say, like, which phenomena, when do phenomena have these spatial temporal interactions, and which phenomena do not have spatial temporal interactions? Could you say something about typical phenomena where you don't need this, and typical other phenomena that have these interactions?
Yes. For example, in hydrology, the product sum model, which is the separable model, is very common. which is because in this case is the spatial structure, the spatial covariance is proportional with respect to the different times.
Mm-hmm.
For example, in environmental sciences, I can tell you that, for example, PM10 is always non-separable and is always negative non-separable. If you compute the non-separability index for PM10 in Germany, and the PM10 in Italy, and PM10 in Apulia region, and you get always a non-separable model which is uniform negative.
And is this an experience? Or
yes, it's an experience. Yes, this is an experience. For example,
what makes PM10 having negative interactions?
Yes, it is a negative empirically. I'm telling you empirically. For example, a meteorological variable, for example, temperature. For temperature, for example, I get from different case studies, from different data sets, that the models required is non-separable and uniform positive non-separable.
Okay.
So
I'm very sorry.
it is common for this kind of
yes. I'm very sorry. We have to stop. The time is up.
Yeah, so, the time is up. So thank you, Sandra,
thank you
very
so much. Yes.
Thank you for inviting me
for this interesting presentation, and also thank you for very well preparing the question on the hackathon. I hope that people have really made an effort there.
Yes.
Having said that, we have now to continue because it is quarter past. Continue to the next speaker, and it is an enormous pleasure and honor that Gilberto Camara actually accepted the invitation to present his recent work to us. Gilberto Camara is professor and researcher at the Brazilian National Institute for Space Research, INPE, and is also the former director of GEO, the Group of Earth Observations, the Geosecretariat. He is an active R user and also developer, and has a strong interest in classifying land use change from remote sensing time series. The topic he will talk about is classifying remote sensing time series with SITS, where SITS is the R package that does all this. Gilberto, are you around, and can you share the screen?
Yes, I am around. Good morning, Edsa. Good morning, Tom. Good morning, Valentina, Hannah, everyone. Many thanks to you for inviting me. So let me go straight. Slideshow. Let's see. I hope you can see my screen now. Are you seeing the one with the show one? Okay. So I'm going to give you a short presentation, hopefully on a package called SITS, which is under active development, and which will be presented here at the OpenGeoHub GeoSchool. So a lot of the discussion was anticipated by the excellent work of Marius Appel. So I'm referring lots of it to what Marius has been talking about data in the cloud. So essentially what we have is data space agencies now are putting more and more of data in the cloud repositories. Google is one of them, Amazon, Microsoft, Copernicus, Dias, and so on. And the goal here is to use the cloud as much as possible. There are problems to it because, of course, you have to have accounts on the clouds and so on, but you have to address the issues. So our perspective here is to develop a package that will allow users to make full use of the data which is available. This essentially means trying to use as much data as possible. Normally, a lot of the use of, let's say, multi-year comparison with the Earth observation data is called what I talk space first, time later. You go to Google Earth Engine and you select one image that is supposed to be representative for a given year, and you classify it. And then you take an image from a second year and you classify it, and then you compare results in time. And what we approach is something we call time first, space later. We take all instances of time, we try to discard try to use as much information as possible, classify the time series, and then join the results of the time series to get the maps. Why time series? Because time series are important to measure change. Some issues in land cannot be adequately captured by just looking at one image. For example, if we look at this image, you can see some areas here which essentially, for example, you see the green and you see the high NDVI in the middle, which is clearly a forest. But if you look at that image there, you cannot just by looking at it tell what is there until you get the time series and you realize, let's say the one which I'm showing in blue in the top, that this time series of, let's say, NDVI has a variation in time, which is typical of crops, in this case, double cropping. In other words, you plant, you sow, and then you cut, and then you plant again, and then you cut again, and then you repeat the cycle year by year. And this is much better captured by a time series. And of course, if you want to capture transitions, time series are also important. What is the typical use of land classification using time series? The typical use is that you get a series of satellite images, you derive the profiles of typical time series, in other words, the ones that, let's say, are the prototypes and the samples that are representative of the classes that we want to use. And then you use algorithms that process this time series to get a land cover map. And there are many algorithms and many different algorithms. I'm not going detail to it. I point some on the literature in my presentation. What does SITS aim to? SITS aims to support the full cycle of a land classification. So it starts from a data cube, and thanks, Marius, for defining what a data cube is. There's a very nice paper by Marius and Answer about Earth's observational data cubes, which have nice definitions what a data cube is. You will extract some samples of the data cube, especially that you basically used to training the models. But we know, and let me show you, that the choice of the machine learning model to classify the data is less important by far than the quality of the samples. So we also have developed packages that parts of the SITS package that uses techniques such as self-organizing maps to do quality analysis of the data and to throw out samples which are not good and to see what samples are good enough. And after doing some quality analysis, you can then run a machine learning model. And after the machine learning model, you can apply some post-processing, doing some smoothing, and that's leading to the final map. So typically, the workflow you would collect, you will select or build a data cube. You will select the samples based on known points where you know where it is. You do the training and you get the classification. Okay, what is a data cube? This is a very important question because I think it's good that in the R community, Marius, Sedza, and myself have used similar definitions or the same definitions. For us, a data cube is a regular partition of space and time. So, and this is not, let me repeat, this is not what you get when you simply access a bucket in EC2, for example, in Amazon, or you access database in Digital Earth Africa, or you access data which is in Microsoft Planetary Computing. What you get there is what they call analysis-ready data image collection, which each image is corrected to account for the day of the year, the sun angle, the atmospheric problems, and including cloud information. But it does not necessarily, all images do not necessarily cover the same point in time. I'll show you an example in a little while. And therefore, it is only by building data cubes that you can do selection on either time series that really refers to the same point in time, or select a layer, but you can be sure that they belong to regular partitions. And we use in SITS, and I'm thankful very much for the work of Marius and Edza, we use the GDAL cubes in SITS. So GDAL cubes package is actually used heavily in SITS. So we have an API. I'm just going to say we've tried to do the API as simple as possible. The proof of the pudding is in using it, but we've tried really to reduce the amount of comments you have to learn, and that will get more clear as we demonstrate. The current point here is to talk about how many R objects do you need to do that. We need a cube, and this is also similar to Marius. We need samples, which is essentially time series with temporal information, and they are archived in a very similar format as the one Edza uses for the SF package. Only instead of geometry, we have time series. We have the abstraction of a model, which can be any model that classifies data, which is trained with the sample. So models include deep learning, temporal convolution neural networks, random forest, and we have the abstraction of a probability cube, which is the result of the classification that says for each pixel, for each class, what's the probability of that pixel belongs to that class, which then is labeled. So these are the 4 objects we have, and they are, let's say, everything around SITS is by modifying, plotting, analyzing, working with these 4 R objects. And again, thanks Marius for describing what stack is and saving me a lot of time. Stack is an abstraction that we use in SITS to access whatever data is there. So Brazil Data Cube, Digital Earth Africa, Earth on AWS, Microsoft, CIPO not yet, but all the others have a stack endpoints. So we use the stack endpoints to have a unique interface to all of this. And essentially, this is the function you call a SITS. You build a cube by, say, calling the function SITS cube. And you say, well, my source is Microsoft, AWS, or local data. This is the name. These are the tiles that I want. This is the start date. This is the end date and resolution. So the single function. And for Microsoft, you replace, for example, the source by Microsoft. If Microsoft follows the same tiling system, which it does, then they will connect to the end stack endpoint in Microsoft and get you a cube there. So we're just the idea is to have the API the smallest number of API functions we can. The other, like I said, just to remind you, we have the objects. So cube is an object that you create by either referring to a set of files or by pointing to a stack endpoint. Samples are a set of time series. So typically, I'm going to show you, but if you take a sample, you will remember, if you know a little bit about SF, is very similar to the SF format. There's a latitude, longitude, and then there's a start date, a cube. And instead of geometry, you have the time series. You can plot it, you can see it, and everything. But it is an object that is different from the cube. There's a cube and there's a samples. And we do a lot and emphasize a lot of the work about testing whether samples are good or not. There's a paper about it. It's all in the documentation. I'm just going to say that this is a very important part of any land use classification, is assessing the quality of the samples. And this is a very interesting.
Gilberto, if I may interrupt you, you say assessing the quality of samples. How do you assess the quality of sample? Are you using some statistical method or?
Yeah, we assess. Okay, so this is the example. So here, what you do a dimensionality reduction. So let's suppose these have, let's say, 7 bands plus NDVI and EVI, so that's 9 bands. So you have 9 dimensions in general, and if you have 23 data points, you have 9 times 23, so you have 100. Your dimensional space is 100 dimensional space. What the self-organized maps do, they reduce it to 2 dimensions. So it's a dimensionality reduction. And essentially here, what you see is the samples clustered. So you have the neurons on these are the neurons of the SOM map. And then the colors, Tom, are the class, the most, let's say, the class of most of the samples that fall in the neuron. Okay, so all the blues are of mostly soy corns. All the, let's say, yellows are rocky savannas. All the reds are soy cotton, and so on. And then you look and find, look, I have some samples. Look at this 14 here. They should all belong together, right? If the samples are from the same class, you expect them to be close in the sum space because they're similar in the properties. So when you see a sample which is outside the typical cluster, this is a point that you should pay attention. And what is behind all this? Behind all this is this all of these samples are from the same class, soy corn. Okay, now let's say magenta samples, the purple samples are from Nero 240. That's the one shown in the top. Okay, and then Nero 240, this is the median of the samples, shows a very strong point of agriculture from end of the year, typical end of the year, which is soy. And then this is cut, and then there is a strong cut again, which is a corn. So you have 2 crops here. And these crops are located in the state of Mato Grosso. You see all the purple samples here? And then you see the other Neuron 14, the one which is far from this one, which is down here in the left corner. Can you see those, Tom? Okay. And then you say, where are these guys? Ah, these guys are in a different place. Are they wrong? Not necessarily, because the climate is different in this region, and therefore the cotton does not grow as strong. The first crop is strong, I mean, you get essentially rain in the end of the year, but there is a stronger dry season which starts in April. Therefore, the corn that grows in this part of the Brazil where the yellow samples are is different. It's not so strong, and the productivity is not so good as the one which is on this part of Brazil. So all of these, the guy said, oh, it's soy corn. Yes, it's soy corn, but the actual results of the soy corn are different. That's what you want to understand, the relationship between the data and the ecology. And ecology always wins. That's the kind of thing you want to do. You don't want to get just your data and say, look, this is my data, and do some training. You want to understand which place, if you're dealing with samples from big areas, what are local differences, ecological differences between those? So you need techniques to do that. Was it okay, Tom?
Yes, sure.
Okay.
And
Okay.
if I may ask also, this the plot you showed, it's through the time, so it's like a curve through time, but you could add an extra dimension, which is in different spectral bands, right?
Yeah, I think this is just band NDVI. We could plot in different bands. I just put NDVI because.
But then it will be difficult to visualize. You will have like a 3-dimensional surface.
Yeah. So it's
anyway. Sorry for interrupting.
No, it's easier to understand the differences. And this is the SOM map. Okay. Now, as for so you have the samples, and then you do the training. Again, we have a single command. Instead of writing, those of you who write deep learning may understand that you have to use Keras or TensorFlow, or you have to understand what is PyTorch. And here, you just don't have to understand anything. You just write sitstring and say, I'm sorry, my data, oh, whoops, this is getting ahead of me. So my data is this one, and the method is this one. And you can, of course, pass a lot of parameters that are typical, and what is the learning rate, and so on and so forth. But the defaults ensure you that you have something reasonable. And this is a recent paper. This is a collaborator of us, Charlotte Pelletier, which is temp CNN for the classification of satellite unit time series. So this is the typical thing that you not run on Google. And the other model is ResNet for it. There are there's 14 models, but the idea is to show, most of all, that we have a single interface, so no vice users don't need to write Keras, which is the current state that people start using Keras or PyTorch. No, you just write sitstring, give me the method, and if you replace ResNet here by random forest, you get a model. And then you send the model for processing. And if you have lots of areas, we have developed in R I love R. One of the few things which I don't like much about R is the parallel processing. It's hard. But we developed something with workers and a lot of machines to how to use this on a virtual machine in such a way that you get a merge map. So we had to customize. None of the standard packages like the parallel or the snow would give us what we want. So we had to do extra work on top of that to ensure that you process the chunks and you get the main process. And in the end, it turns out that this is similar to what Google Earth Engine does. You break the image into chunks. Only in the case of Google Earth Engine, the hundreds of chunks. These are typical 8, 20, or 24, depending on the machine. And after the classification, typically you get some noise because of the time series in time, so you have to do some spatial post-processing. We offer some filters, including a new filter we developed with Bayesian smoothing, so you get some smoothing done using Bayesian analysis. And the other point we made is 95%, maybe exaggerating, 85% of the papers published on remote sensing journals and similar use k-fold validation to assess the quality of the model. And this is plain wrong, because the validation only validates, because you k-fold validation, you take the same samples that I used to train to validate the trained model. So you just know that you're not wrong, but you don't know how right you are. So the community has developed what they call a good practices for estimating area and assessing accuracy of land change. And this has been used by FAO, a map accuracy assessment, and we have implemented the so-called best practices as in SITS. And some examples, here is a real life example. So it's take 200 million hectares of the Cerrado. These are basically 46 Landsat images. We took 48,850 samples. Don't be surprised, this is a typical thing. You want to represent a large ecosystem with a huge gradient, almost coming to it's almost ranging from the whole tropical area, from the equator to the Capricorn Tropic. And we use the temp CNN model, which is this one time series for convolutional neural networks, Landsat 8 16-day time series, and we processed 8 terabytes in 24 hours. The training took 3 hours and the processing something 22 hours. And we get 10 classes for a huge region with 85% global accuracy. And for deforestation, we're getting on tops of 90% real accuracy. So in the case here, I mean, this is in Brazil, where you see the results from temp CNN, random forest, and ResNet. And typically, you can see the Sentinel for 1 year. This is the red area. So the black here, or the dark green is forest, And obviously, you see that's no longer dark green after 1 year, which are the forested areas. And you can see similar where I don't know if you can see my mouse, but this was a forest that was deforested and it's collected here. So the results are quite good. So enough said, let's look at the examples. So my point here is the best place to learn SITs is the book. So the book. Sorry. So there is a book. It's not finished yet, but I'm following the footsteps of Jacob and Edza. We're developing a book using Markdown. So I think I sent you the link to the book. It's an ongoing work, but it describes the current version. So I'm going to go, and so there's chapters here. It's essentially the same kind of thing that we have in Jacob's and Edza. Have an introduction and then a discussion on data cubes. So there's a working data cubes and discussing the working in time series, a time series clustering, and so on, classification. So it's a work in progress, but it's already, I hope that you can benefit from it. If you want to know more, in the book itself, there's the references from SITs and that you can get. So there's the references, and of course, we thank these authors here, Edza, Marius, Hassan, Verens, for the packages we use. Right. So I will then use the Markdown. Where's my Markdown? Okay, so I'm going to run things on my Markdown because they are essentially the same of the book. Tom Hengel, does SITs maybe supports ensemble ML? Not yet. What if you smoothing reduces mapping accuracy? You don't do smoothing in this case. Shouldn't be careful about smoothing just to make the map more simple. Yes, you can apply or you cannot apply. In the sum clustering, what type of dissimilarity measure you use? I think you can select it. Currently is Euclidean. Kamal, what engines does SIT support use for its machine learning? Basically, it's scarce. Does it use ML packages like tidy models or Carrot? Well, basically, they don't work with neither tidy models nor Carrot. Currently do what we need to do. And essentially, I mean, let me put it this. If you don't want to use deep learning, you use random forest or XGBoost and you get a good result. Then if you want to do deep learning, you can use the typical deep learning, but convolutional neural networks and attention networks are all the rage right now. So I'm not sure we need to include more engines for machine learning, but that's a discussion we can have later on. So now what I'm going to do, so I'm following your Mattermost here. So I am going to go into the introduction. So as you can see, let me make sure I clean the environment. So I'm in RStudio with the same copy that you could get on the book. Okay. So now you can have, and I hope you all have downloaded. So let me clean the console as well. I hope that you all have downloaded the companion package, which is called SITS Data. SITS Data, it's because CRAN will not allow us to have lots of data, so we had to build a package to do some interesting examples. So we're going to create a cube. We're going to create a cube based on local files. Now, the problem with local files is that you don't have stack. So what do you do? So in SITS, now I'm having SITS here just for your information. If you want to use local files, you can. Which one is Modis? Synop. So if you want to use local files, you can, but you have to tell SITS what your files are. Let me make it bigger so you can see some names here. Let's see. Because there is no way to tell in currently in standard JPEG files or TIFF files what your data is. So you have to give us some hints of what the tile is, what's the band, and what's the date. And you can put this in any order as long as they're separated for some kind of delimiter. The idea of using this, it's because Sentinel uses this convention and Landsat uses this convention of getting names with delimiters. So we're not, so view, let me wait. So active size, okay, back. Is the size okay for you? Can you want me to make it bigger? Okay, so you see here, it's a local file and the parse info. So parse info is, oh, where's, I mean, you can have a name with 20 steps, but where is the location of the tile, the band, and the date? And then once you have it, you have a data cube. So a data cube in SITS is a tibble, if you know what a tibble is. Data cube in SITS is a tibble, and this tibble is basically has a lot of information. And there is one thing here, if you want to get, called file info, which is basically the information on the file. It's contained there. It's the links. And in this case, you can see that this is a place in R because this is an internal package, but you get basically a tile, date, and band. And you can ask things like, what's the timeline of this cube? So you see immediately that it has 18, 19, 20, 21, 23 time steps ranging from 14 of 9 to 28 of 14th of September to 28th of August in the next year. And then you can use, and thanks Adza, because I'm using stars here, I'm plotting. So this is the, you plot, I don't know how to plot color images in stars, but that's my fault, not Adza's. So this is EVI band for time one, and you can plot them. So you have a data cube. So you can follow it. This is basically standard on the book. So I'm going from book to book. So if you have any questions, a beginning question. Let's suppose I start with GE for cloud data acquisition, then connect with R with RGE. No, because RGE just is like a front end to the Google API. The SITS API is different from the Google API. For example, the SITS train, you don't have an equivalent. Because, for example, we do training with functions that do not exist in the Google API, such as deep learning. And Google doesn't use the same comments as we do. For example, so these are the samples. So now I told you that we have a cube and we have samples. Okay, so this is basically samples we're going to use to train a model. So if how many samples are there? If you just type samples, Mato Grosso Mood 13 key one, you have 1,892 samples because there are 10 that just shown. You can, for example, you can plot them, or you can say how many bands do I have in these samples? Samples, Cerrado, Mato Grosso. You have NDVI, VI, near infrared, middle infrared, for example. What's the time series? Should be the same as the cube. So you can verify that the timeline hopefully is the same as the cube. Yes, we have 32. Okay, now we have two structres. One table, which contains the time series, and the cube. And then you can say, okay, I want to see these guys. Okay, so I'm gonna, oh, there's a bug here. Samples pastures, samples forest. So I'm selecting here So essentially what I did here was, it should be samples forest. Thank you for, it's good to teach because you find bugs. So this should be samples forest and DVI, and samples forest and DVI. Right. So what you have here is basically you filtered with the clear all those samples with label as a florist. Okay, fair enough. And then you you selected the NDVI band, and then you plot. And then you see that the bar here, this is brown bar, is the median. And the upper bar is the third interquartile range, and the lower bar is the first interquartile range. Note that we use median and interquartile range because of robust statistics. You ask Edza if you want to know more, or Hannah Meyer, people who know about these things than me.
Gilberto, I missed the overlay. I missed the overlay. How did you get the values from the cube? That's pre-prepared.
That's pre-prepared.
Okay.
I can show you in a moment. But that's fine, no problem. So let me show.
It's a space-time overlay, so it's interesting.
No. Okay, let me show you. Let me show you in another example, and it helps me to get. Okay, so a second example. Okay, second example. This is another real example. Now I'm in Amazon. Okay, and I am selecting a cube. So let me stop this. Stop. Mute. Debug session interrupter. Did it interrupt? Thinking seriously about me. Restart. I'm restarting R here. Okay. Restarting our session in my machine. Clean the environment. Okay. Now, let me just do something which I hope that this goes so fast. Okay. Marius has already explained to you that this is, you have to have this secret ID, default ID to get into Amazon. So this is mine, I'm going to erase it. But now let's go to Amazon. So now this is a real example. Oops. Okay, so now I am going to Amazon, getting 2 cubes, you see, 2 tiles from the Sentinel with lots of bands, and for 1 year. And now it read the cubes using the stack. So if you type S2 cubes, it has 2 lines. One line is the first tile, the second line is the second tile. So far, so good. But then you run into a problem. Its timeline is 2 cube. The first tile, T20LKP, has 67, 68, 69, 70, 71 time steps. The second tile has 140, 41, 42, 43, 44. So you're in trouble. And that's what you get from Amazon. You get 2 neighboring tiles with different time steps. What you have to do, Marius, this is Marius. You regularize the data cube. So sits regularize calls GDAL cubes. So if you know GDAL cubes, you know sits regularize. So basically it says, now take this first cube, get me a regular cube with a period of 16 days, median as aggregation, resampling by linear, and I have a cloud mask. And it takes, of course, I'm not going to run because It runs a lot, but in the end, it produces a set of regular files. Lots of files. Okay, now these are local files. Now, beautiful S2 regular cube is, I'm not doing this on, I had prepared it for the demo, right? So this is the cube, GDAL cubes created for me. Now, if I do sits timeline S2 regular cube 1, lo and behold, I have 20, 21, 23, 23, 24. This is what I asked for every 16 days. And if I do the second tile, the same. Thank you, Marius. Now, all of this to answer Tom's question. Now, I am prepared to get the samples. What do you want to do to get the samples? You need a script, either set of shape files you get from SF or a CSV. A CSV. A CSV says latitude, longitude, start date, and date label. You can run it from the shape file as well. So this is what the user gives Tom: latitude, longitude, and date, and label. And now I get the data. I say, give me the regular samples from my data. Did I answer your question?
Yeah, so that's the space-time overlay, basically.
That's the space-time. Yeah, that's the space-time. I get the samples, right? And then I start. So let me go back to the book. So you now back to the samples. I have already got
the values that when you overlay, you do this median, right? So when you have
no, wait. Oh, okay, step by step. When I create a regular cube using GDAL cubes, remember, I had in the beginning 2 tiles with completely different timelines. One had, for the same period of time, the frequency of the images are different. This is what you get in Amazon, and that's true in general for any Sentinel or Landsat, especially Sentinel. So the first tile, L20 LKP, it has an acquisition of 13 of July. The next acquisition may be Sentinel 18. The next one, 23 of July, for this one tile. Now, the other tile starts at 13 of July. Then there's an acquisition on the 15th, which this one doesn't have. And then the other acquisition is on the 28th, but this guy has on the 20th. It's the characteristics of the satellite. So these are analysis-ready data, but these are not data cubes. So if I want to use one tile is consistent with itself, but 2 tiles are not consistent with itself. So let me go just to finish the classification and start the questions. So that's why, Tom, I have to regularize the cubes. And then I get 16 days using a median value. And if you want to understand what the median value works, please go to the documentation of GDAL cubes. And then I get a regular cube that I can do a classification. Okay? Now, so let me go back to finish the story. So I have now the samples, a regular cube, and now I'm going to select. I'm going to just to be fast, I'm going to select 2 bands. So I select 2 bands, and like I said, I train a model. So here, what I'm doing is that train with my data sets a training model. In this case, temp CNN, one-dimensional convolutional neural network, which is Charlotte Pelletier's model, which is pretty good, close to the state of the art that you can get. So it's training, it's doing some work, and it's going to finish, then you can plot it. And then, hopefully, and then you can do the classification. So we just have to wait, hopefully less than a minute. I hope it does. Or I'm sure I have there lots of questions in the chat, so in the Q&A as well. What? Just because it's a demo, it won't work. Oops. Do we have to wait? Let me see some of the questions. Del Conte do wonder me. If I saw you, it sits work on our version 3. No, we're not committed at this point to work on version 3. We work on version 4.1. 4.0 works, but we recommend the latest version. Remember, it's not on CRAN yet because we're just on development. So we have a temp CNN model. And this is the result. This is the plot of the result. So it shows that it has converged fast. Again, it's testing against itself, right? So essentially, it's the training data and the validation are very close. We have a model. How good it's not bad. And then you ask the system, again, simple interface, classify the data using that model. And then you classify the data using the model, and you have, you're gonna have soon a result. Okay, you have the result. And then to plot the probabilities, I am going essentially, this is, as we recognize it, because this is a stars plot. So what do I get in the plot? What I get in the plot is the output of the machine learning model. So here, it's the, on a scale of 0 to 10,000 or 0 to 1, the likelihood of each pixel being a forest and the likelihood of each pixel being a pasture. So these are probabilities. For the same pixel, I have a set of probabilities. I could do, Tom, directly the land map. That's what Google does. But if you have the probabilities, you can derive uncertainties, you can do a lot. And in particular, you can do the spatial smoothing. So here I can, for example, smooth the probabilities and plot. And maybe you can see that it looks nicer. Maybe Tom doesn't like that it's nicer, but it's your choice whether you want to do the smoothing or not.
I just want, the look good and the accuracy. If I have to choose, I choose the accuracy. So if the smoothing decreases accuracy,
in general, it increases accuracy because it basically, it's a long story, but it does a Bayesian estimation of the thing. So it's in statistical terms, it should improve the accuracy. That's what we do. And finally, you can label. Label means that you do the labeling classification. So here, you plot the label. Again, this is basically the classes and the labels. Of course, you can save that and put in QGs because CNOP label, all of these are cubes. So CNOP label is a cube. And the CNOP label $file info has the location that you can, this is on temp, that you can save wherever you want. And that's it. I think it's enough for the demo, and everything is on on the book, so I can tell you that please go to the book. So I think I could now stop the sharing and ask the Q&A or the Mattermost. Let me see what the Mattermost is saying. Mattermost.
Edgar will read the questions, by the way. He collected the questions for you, so he will pass on.
Okay.
Well, I think you answered most of them now, Rebecca, so we could have a somewhat more. Let me see if there are still open questions. Where did you... so you answered one from Tom, right? Does SITS maybe support ensemble ML?
Not yet.
The GE question you answered. Then there's a question, but how to generate the sample data if the dates in the samples do not fit the dates of the regular cube generated? I had the same question. Okay,
first of all, let's look at the dates in the samples. Okay, let me share the screen again. Okay, now let me show you. Well, not this one. So what do you have typically is samples, this one. Samples, this one, U5. Okay. What you have to tell SITS is the start date and the end date.
So it's segment, it's periods.
It's periods.
The training data are periods, okay.
Periods. So within that period, it will get whatever it, so if the data cube has 100 images in this period, the time series will get 100 values per band. If it has 50, it gets 50 values. If it has 20, get 20 values. You just tell, wait, I want to start here and start here. And you basically, if the data cube has more, it will only collect within that period. So it basically, the samples dominate everything. Yes, Tom?
Yeah, so when you do this aggregation, you do a median. Have you tried also taking like a standard deviation of the values in the span? Like maybe that could also help increase the accuracy.
Well, that's the 2 points. One is what happens when you do this this regularization. This is a good debate. What I have done is I relied on the work of Marius and Edza, because I think that's the basic principle of R. If there is a package that does something you want, use it. Don't. So we basically.
But you need to make decisions there. So you need to parameterize there. There will be defaults, but you choose how GDAL cubes aggregates, compute mean or medians of something.
Right. What we've seen is median is a good parameter in general, but we cannot at this point. We're not making, Tom, any very strong assertions. I think what we see is what controls the quality of the things is not whether we have got good results of regularized data cubes, 16-day data cubes. What controls the accuracy is whether your samples can reproduce ecology. So remember, this is the crucial bit. All the rest is really, really, I would argue, all the rest is not important. Right, let's just remember the following. If you're getting a huge area in Brazil, like the Cerrado, who covers from the equator to the Capricorn, if you only collect samples in one place and try to classify somewhere else, it's not a given that your samples will represent what the data from this somewhere else will go. So in this sense, the median values are not because the overall let's say, shape of the curve is the one who is controlling the accuracy, shape of the curve, and of course the variations. I can tell you that's, for the moment, my answer.
Okay. Are there any other questions right now?
Is quality analysis a manual process or automatic in SITS? Well, it's automatic to the extent that you have the tools and you can do it automatically. I never say, I mean, if you look at the documentation on the SOMMAP, you can actually run the whole process automatically without looking at the data. I don't recommend it to you. I really recommend, my sense is you have to live with the data. You have to live with your data. You have to go to bed with it. You have to understand it. Seriously, because you are dealing with ecology. It's not people's faces. It's not dogs. It's ecology. It's ecological variations of ecosystems that you're trying to capture. It's something that you have to understand very well the realities on the ground. There's no miracle here. Tom?
Yeah, I wanted to ask, like, some of this programming, I mean, I really like it with SIS. It's like, it's kind of like you made like a wrappers and you go in like a 4 lines, you know, you could overlay train model and get the map. So it really enables people. But what about the computing time? I mean, you could make some code like you show with your book. I mean, it can go like a 1 minute. Do you have some way to, before people start computing, that they estimate a complexity of computing, and so that they don't jump into computing and leave it like running for 10 hours or something? Is there any tools for that?
Not yet. That's a very good point. And but I just want to show one final bit here, which I think it's important for you to understand. Let's see if I have a.
I mean, the simplest thing will be a progress bar, but it's even better to have kind of a function that estimates what will be a computing time or complexity or.
Well, I'm sure. I mean, this is obviously a very good point. What I'm telling you is I'm not sure we have it at the moment. No, I'm sure we don't have it. Let's put it this way. But what I wanted to show you is something else. Let me show you the following. Where is it? Gosh, I get many things at once. This is an example I like to show a lot, which is the following. The question here is, how many lines of code do you need to classify a region of 200 million hectares, right? With the state-of-the-art, classifier. Okay, so it turns out to be 1, 2, 3, 4, 5, 6. So this is all it takes to classify 200 million hectares. So you define a cube in the Brazilian data cube as Landsat. You pass on a region of interest. So you say, I want the shapefile of the Cerrado. I have the samples, okay, CSV, get me the samples. So SITS get data, SITS cube, SITS train the model using a temp CNN network, classify using this model here, calculate the probabilities, and label the classification, and you get this. 200 million hectares, 24 hours of processing, 3 hours of training, 6 R comments. I think it's hard to beat. You can do better. But in less lines of code, I'm betting that not even Google Earth Engine does. Certainly it doesn't, because it has not temp CNN. It doesn't have a stack interface. So a lot of work, Tom, went into the API, a lot of thinking. We spent a lot of time considering how best to have an API that meets complexity, but sort of encapsulate a lot of the things we do.
So Google Earth Engine has a stack API. I'm not sure whether it can deal with time series data with these segments,
not well.
classify time series in such a way. So that is a really cool feature, I think.
And the other, it cannot use any kind of deep learning technique. For example, this temporal, you have to export all data into the Google AI platform, and then
Okay.
and then you have to write. The point here is you have to write the code in Python or JavaScript to get the result. So you have to really write the internal Keras code.
There is this last question on Slack that on Mattermost. Which deep learning algorithms are available in SITS besides STEMP, CNN, and ResNet? Any 2D or 3D CNN?
No 2D, not 2D at the moment, because we're just using time series. So you go for 1D. We have, of course, XGBoost, the traditional ones, XGBoost, Random Forest, and SPM, and then the multi-layer perceptron. We're working on attention networks, but it's not an easy one. We're discussing whether it is worth going to 3D CNN. It's something to be discussed, but of course.
Does that mean like you have time and sort of neighboring pixels that you look at in one?
Yeah, that's what we're looking. I mean, TIMP CNN is 1D, so it does filtering nicely, and ResNet is also time series analysis.
Because you basically use now this Bayesian post filtering, right? Where you basically say, if I have speckles, then I'm going to sort of smooth them out.
Right.
That kind of cuts the time processing and the spatial post-processing into separate processes where you...
Yes, exactly.
Ideally, you would sort of do that in one, I guess you would like to do a single model or so, right?
That's why we call it time first, space later.
Yeah, but ideally you would sort of do it at the same time.
Ideally,
I'm very sorry, we have to stop. I'm very
Okay.
sorry, the time has run out.
Oh, I'm getting carried away. Yeah. Thank you
Okay,
so
we
much.
have to stop. Thank
for
you
a
so
great
much.
presentation.